Hi everybody, happy Friday. This is Unit 3, Lesson 4, and we're going to be learning how to write nuclear reactions, transmutation reactions, and we're going to learn how to fill in the missing particle. So you will have to write them straight from words, or you'll have to know what the unknown particle is, and I'll walk you through them. It's really actually pretty simplistic. You can recognize a nuclear reaction from an ordinary chemical reaction because in nuclear reactions, if you look at these, they always give you like little atomic mass and atomic number. And ordinary chemical reactions won't do that. So that's how we know we have a nuclear equation. But you might get a question like example 1 here in your notes where it says, what particle is represented by X in the equation? So they want to know what X is. The key to doing these is that mass and atomic number, if you will, are conserved. So whatever the total mass is on the left side of the arrow, which in this example happens to be 28, that must also equal the total mass on the unknown or the right side of the arrow. So when I add together the mass of X and the mass of Na, they must equal 28. The same thing is true for your bottom numbers. So if you go to this side that doesn't have the X and you add up the bottom numbers, 13 and 0 will give you 13. So when you add these bottom numbers, they must equal 13. So let's get the top number of X. What can you add to 24 that will give you 28? 24 plus what equals 28? And that what is a 4, right? 24 plus 4 will give you 28. Same thing from the bottom. 11 plus what will give you 13? That would be a 2. So now you would go to your reference tables and look up the symbol that goes with a bottom number of 2 and a top number of 4, and that would be He. So this is an example of alpha decay, but your missing particle is this. That's your answer. That's all you do. Oh, sorry. So if we go to the next one, example number 2, which isotope is represented by X when the following equation is balanced? Okay? So we draw a wall where our arrow is. We go to the side that does not have the X, and we add up the top numbers. And this time they equal 18, which means when I add up these top numbers, they have to equal 18. Right now you have a 1. What can you add to 1 that will give you 18? That's right, 17. And you do the same thing with the bottom number. 7 plus 2 gives you 9. What can you add to 1 that would give you 9? That's right, 8. So now we're going to go to the periodic table and look up the symbol that goes with the atomic number of 8. And it should be oxygen. So your missing particle is an isotope or atom of oxygen. Okay? The other way they can do this is like example 3. Write a balanced nuclear equation for the positron emission of Al24. So, not just fill in the missing particle. This takes it one step further. This is our isotope. That's who we will start with. So Al has a mass of 24. I go to the periodic table. I look up aluminum's atomic number. It's 13. It is decaying, so you don't have anything else on the left with it. How is it decaying? It's emitting a positron. So I am going to have a positron as one of my products. If you've forgotten what the notation is for a positron, you can always go here to table O. And this, if you look at table O, if I could get it all on the screen, that'd be lovely. There you go. So this is your positron, that's your notation, okay? So if I go back here and I write the reaction for the positron emission, I have a positron as a product. And then, again, something else, because right now my top numbers don't equal. I have a top number of 24 over here, so I know there'll be a particle on the right that also has a mass of 24, so that 24 and 0 give me 24. My bottom number over here is 13, So my missing particle has to have a bottom number of 12, so that 12 plus 1 add up to 13. And then I would go and look up the element that has a bottom number of 12, and it's magnesium. Okay? We'll do the same thing with the next example. Write the balanced nuclear equation for the beta decay of Si-35. Just going to move this little box over so you can see the whole question. There we go. So we start with our Si-35. We look up Si's atomic number, and it's 14. This time, it's undergoing beta decay. So we draw our arrow, and we write the notation for a beta particle. Draw where your arrow is. The total top number over here is 35, so there will be another particle on this side that has a mass of 35, because 35 and 0 gives you 35. The total bottom number over here is 14, so there will be a particle on this side whose atomic number is 15, because 15 minus 1 gives you 14. You look up what symbol is 15, and that is phosphorus. Okay? So on a separate sheet of paper, if you would, I would like you to do on here number 1 and number 3. Will you please write the reactions for the beta decay of Pb210 and the alpha decay of Rn22? That must be done on a sheet of paper, a separate sheet of paper, because I will ask you to turn that in on Monday. That's it for today, everybody. Have a great weekend, and I'll see you on Monday. Bye-bye.